start the recording. So this lecture is being recorded. So you're being recorded, and you know, you all remember solving systems of equations. How many remember that? So this relates to section 1.1, what I'm talking about here. Systems of equations. How many remember solving systems of equations in algebra 2? How many remember doing that in algebra 2? You know, you have let me just see here. Sure, Mikhail remembers that. You have some system of equations, okay, like this. And the two equations in this case represent the equations of what? What would each equation, thank you, what would each equation represent geometrically? X plus 2y equals 1, negative 3x plus y equals 4. Those are good. That's right, Mikhail. Those are two lines. And you're trying to see if the two lines intersect, or they may not intersect. But you have to solve the system of equations. So you basically, the two lines, if they intersected, well, they could intersect, they could be the same line, and that would mean they intersect at all points. That's not going to be the case with these two lines. The two lines could not intersect, or the two lines could intersect in one point, one coordinate xy point. So you're looking to find the xy coordinates, and to do that you have to do some reduction on the equations. So when you have a system of equations, what can you do? Well, you have to eliminate one of the variables from one of the equations using the other equation. So like here, you'll notice, and let me just see, maybe one moment. Let me put in my stylus here, actually. One moment, give me just one moment to do that. Let me pull that out, hold on. One moment, I just gotta, hold on. Ah, my goodness, so many cords. Sorry, class, just gotta get this, find the cord here, here we go. All right, it's almost like there's an invisible force that tangles the cords up when you do this stuff. So, okay, so we're in here we use the addition subtraction method. So what I'm going to do is I notice here I have a 1x, and here I have a negative 3x. So let's say I wanted to eliminate the negative 3x on the second equation. Well, what I can do is multiply through the first equation, okay, this first equation, by 3. And if I did that, I would get 3x plus 6y equals 3. Okay, so you know, if you multiply through a 3 through by the first equation, x plus 2y equals 1 is the same as 3x plus 6y equals 3. And now what I can do is I can add the two equations together, and the 3x minus the 3x, this part here, when you add that, that's going to get me a 0x in this spot. And therefore the second equation is just 7y equals 7. And so I'll get y equals 1, and then I substitute that back in the first equation. Okay, so this is certainly one way of solving a system of equations. But you learned in algebra 2, when you did this, you would carry the variables around with you in your work. Okay, so this work here on the left side, okay, you're carrying the variables around. Okay, so how many is this a good refresher? How many now recall this? solving system of equations this way. It's maybe been a while. Okay, Cameron does, Zishan does. Wonderful. Well, you see, and Tasmia does, excellent. In linear algebra, thank you, Perchetti does too. In linear algebra, we solve larger systems of equations. Okay, we might solve a system of 3 equations in 3 unknowns, or 4 equations in 4 unknowns, or so you can have 50 equations with a number of unknowns. So we have to have a efficient way to solve a system of equations. And what we can do is we can take the system of equations and write the coefficients and the numbers in a matrix. So this here is a matrix. And what I've done is the coefficients of the first equation are 1 and 2. So I have 1 and 2 here. And then on the right side, I have a 1. So you can imagine some books, what they do when they have what's called a augmented matrix. An augmented matrix. Augmented matrix means the matrix represents a system of equations. And for our book, well, how many have seen like an augmented matrix with like these like dashed lines for an augmented matrix? How many maybe have seen that in another class they've taken, maybe in high school or even here at Montgomery College? I don't know if you've seen that before. I have seen it in other textbooks. Okay, so yeah, a few folks here, Mikhail and David, think they have. Well, in our textbook, they normally don't put the dashed lines there, okay? But this is indeed an augmented matrix. And you see what we're doing here, when we took the first equation and multiplied it by 3 and added it to the second equation to get this system here, we did what's called a row operation. Really what we did was we multiplied the first row, or the first equation, by 3, and then replaced the first row by 3 by that result. So you see the 1, 2, 1 in the first row here, the 1, 2, 1 got replaced with a 3, 6, 3. That just means that x plus 2y equals 1 is equivalent to the equation 3x plus 6y equals 3. So that's called what we call row operation. And we denote the row operation, that row operation, this way. You multiply the first row by 3 and then replace row 1 with that result. Okay, are there any questions so far?
What'd you say was the name of the operation again?
It's called a row operation. That's what we call it. We call it a row operation. Actually, we call it an elementary row operation. I'll write it here. Elementary row operation. Yeah, and in your textbook in section 1.1, they talk about there are 3 different kinds of row operations. This row operation is called a replacement. This is a replacement row operation. Now, what did we do next? We added the first row to the second row. Okay, and I'll try to use different colors here. We added the first row to the second row and put the result in the second row. Okay, that's how we got a 0, 7, 7 in the second row. That just means 0x plus 7y equals 7. So this is, I want to be careful here. Well, it's another type of row operation. I want to be a little bit careful here. Actually, I think I have an error here. This operation up here wasn't a replacement. This operation here, where we did 3 times row 1 and put that result in row 1, that's called scaling. That's called scaling. So let me see if I can just fix that right here. Yeah, that's called scaling. This operation here, where we added the first row to the second row and put the result in the second row, that's called replacement. Let me just be careful here. Yeah, that's called replacement. And then there's another type of row operation called an interchange, where you interchange rows. I don't have that for this example, but in the next example, I'll show you that. So what I wanted to do was just sort of work with a very simple example, something you might have seen in Algebra 2, and show you what's going on with how we are using matrices, augmented matrices, to simulate, to show the row operations. Well, I want to be careful how I phrase it. That we do the row operations, but we don't carry the variables around. We just work with the numbers in the equations. All right, because it'll make our lives easier. And also for computer programming, it's much easier than to just work with matrices. Are there any questions on that? We're not going to go and solve the system. I just wanted to show you a little, introduce you to the idea of these row operations. Okay, are there any questions? Okay, all right. Let me go to an example here. Let me go to an example, and after this example, we'll take our break. Don't worry, but break might be a little later this time around, just because we had to do a little orientation. Let's work with something like this. We're going to solve this system using elementary row operations. And let me give you a moment to copy the example down. So I think it's a good idea. How many do write examples down in their notes? I think we learn when we write examples down. It helps us sort of learn the material better. I always found that to be true. How many of you found that helpful? Okay. Oh, wow. I have like 7 students say that. Great, great. Okay, so I'll give you a chance to copy that down. Now, one thing I'll mention too, in linear algebra, like for this kind of problem, you might, like what you're used to seeing, and is something like this for the first equation, negative 4x plus 5y plus 9z equals negative 9. Okay, and the thing is, we don't want to, there are only 26 letters in the English alphabet, A, B, C, D, all the way up through Z. We don't want to be restricted to that because we might have systems of equations that have 50 variables. So instead of using X, Y, Z, we're going to use X1, X2, and X3 as our variables. Okay, that's by convention. And what would each of these equations represent geometrically? They can't be lines because for a line, we would only have 2 variables.
Could it just be a line in a 3-dimensional space instead?
Well, it want to be a little. It could.
Actually,
and I
I remember those ones are very weird.
All responses are helpful. It can't be a line. It has to be something else. It can't be a line. A plane. That's right. These are all, well, these are all planes here. Good. Let me see. Mikhail and Jonathan. That's right. How many remember maybe in pre-calculus or earlier class of saying equations like negative 4x plus 5y plus 9z equals negative 9 and saying, oh yeah, that's a plane? How many have seen that? Like 2 variables gives you a line, 3 variables gives you a plane. Okay, that's something that I would have hoped you would have seen somewhere along the way. But anyway, these are planes. And we have 3 planes in 3-dimensional space. And if we're trying to solve the system, we want to know if the system is consistent, then the solution would be a point of intersection between these 3 planes. So that's what we're trying to do. We're trying to solve for x1, x2, and x3. And if the system's consistent, we'll get a solution, a point of intersection. So first thing we need to do is we need to write this system of equations as an augmented matrix. So if everybody's good copying this, I'll move to the next page. Are there any questions? Okay. So we're going to use the elementary row operations, and we're going to write the system of equations as an augmented matrix. That's this first matrix right here. Please let me know if you have any questions at all. And remember, this is an augmented matrix. So we you know, again, that dashed line is not drawn in, but we know the matrix represents a system of equations. What are the dimensions of the matrix? How many rows, how many columns? 3, right, 3 by 4. Right, Cameron, right, Mikhail, it's a 3 by 4 matrix. 3 rows, 4 columns. That's right, Perketti. And okay, so what we have to do is we have to simplify this system of equations. We have to break it down so that we can find what the solution is. So how do we do this? How do we do this? Well, what we want to do is, you know, we want to work, well, of the three equations, the third equation, well, let me put it this way. If you had to decide between the first equation and the third equation, which equation appears simpler to you? The first equation 1 or equation 3? I agree, equation 3. And what makes that equation simpler? What's sort of a key number that's making that equation simpler?
The first number is 1.
The first number is 1. That's right. The first number is 1. So you see, what I'm going to do is I'm going to use the third equation. I'm going to use the third equation to help me simplify the system of equations. So I'm going to take that first equation and I'm going to interchange it with the third equation. That's what you see in the second matrix. And this symbol here, this little tilde symbol, means equivalent. So the first system of equations here is equivalent to the second system of equations. They are equivalent systems of equations. Generally, what you would like is you would like to have a 1 traditionally in the top left corner. Okay, and we're going to use that 1. We're going to formally, we call that 1 a pivot. Now we're getting a little bit maybe ahead of ourselves. Pivots and so forth are brought up in section 1.2. But what we want to do with the 1 there is where the -4 is in the third equation, we want there to be a 0 there. So I'm going to take 4, I'm going to multiply through the first equation by 4. That's 4 times the first row. I'm going to add that to the third row, add that result to the third row, and then put the entire result here in the third row. So the third equation is going to be 0x1 minus 3x2 plus 13x3 equals -9. Okay. So like for instance, how did we get the -3 here? How did we get the -3? Well, I took 4 times -2, this -2 here, and then added it to 5. Added it to 5, and that gave me -3. The 13 here, how did I get a 13 there? Well, I took, maybe I'll put it in a different color. How did I get the 13? I took, sorry, hold on here. I took 4 times 1 and added it to 9 to get me the 13. Are there any questions on the third matrix, the third augmented matrix? All right, all right. Well, okay. So now what we want to do is, and this is all recorded, but let me just sort of clear the annotations here. I think you'd agree that the third augmented matrix is simpler than the second augmented matrix, right? Well, and what makes it simpler? What are good numbers to have in our augmented matrix? What makes the system of equations easier to deal with? What numbers do we desire? Yeah, in particular, the goal is to get zeros in the system of equations, 0 entries, right? And ones are nice numbers to help us do that. But you'll notice now in the I want to get a 0 in this spot here. Okay, I want to get a 0 in that spot. So what I'm going to do is I'm going to work with these two. Well, I want to be careful here. I'm going to work with these two equations here, right, to produce a 0 where that, hold on here, where that -3 is. Well, what if I were to multiply the second equation by 3 and the third equation by 2 and add them together? Why do I want to do that? Because 3 times 2 plus 2 times negative 3 equals 0. You see, I'm focused here. I'm focused here on the 2 here and the negative 3 here. Well, 3 times 2 plus 2 times negative 3 gives me this 0. So that's what I do. I'm going to multiply 3 times the second equation plus 2 times the third equation, and then that result goes where the third equation was. Okay, that's elementary row operation. Hold on here. That is a replacement. So you've seen here an interchange, and then you've seen 2 replacements occur. Two replacements. And that gets us down to here. Okay, give you a moment to look at that. One moment. Okay. So what we're doing is you have, when you solve a system of equations, you have what's called a forward phase and then a backward phase. And what we're doing here is the forward phase. So the goal is, again, to get as many zero entries in the augmented matrix as possible. And you notice that the bottom left-hand corner, we have zeros there. So a triangle, a triangle of zeros. So this is what's called triangular form or echelon form. And we're really happy because do we know, can we get one of the variables based on the augmented matrix here, that augmented matrix, can we determine the value of one of the variables? The variables, remember, were x1, x2, and x3. Okay, which variable can we determine? Good.
X3.
X3, because the third equation here is 0x1 plus 0x2 plus 2x3 equals 6. And so x3 equals 3. So that's great. That's great, you know. But we still have 2 other variables to solve for. So it might make sense here in this situation. It might make sense to be, you know, I mean, I could say, okay, x3 equals 2, and then I could take that value and back substitute it in the first 2 equations. But it might make more sense to try to produce some more zeros in the system of equations. Okay, let me just see one moment here. Okay, it might make more sense to do that. So for instance, what if I could possibly produce zeros in this triangle here? I mean, that would be great, because then I could just you know, read off my my values for the variables. That would be amazing. So now what we're going to do is I agree, Mikhail, is what's called the backwards phase. So the backwards phase means, okay, well, one moment here. Now, one moment. Let me just check one thing on this. Hold on, hold on. I want to check one thing before I move forward on this. Just trying to double check everything. Yeah, let's go ahead and this last equation, we have 0, 0, 2, 6. If we were to scale it by multiplying through by a half, we would get 0, 0, 1, 3, right? And there's a 1, and a 1 is a great pivot to use. So let me go to the next page and show you how this works. So here is the matrix that we had, the augmented matrix from before. And what I'm doing here is now I'm going to do scaling. Okay, that's another elementary row operation. The scaling, hold on here, I got a lot of, trying to find the page here. The scaling row operation, that's another elementary row operation. So I'm going to take the third row here and multiply the third row by 1/3, and then take that result and replace it in the third row. That's going to give me a 0, 0, 1, 3. Now I have this 1 here, and that 1 can be used as a pivot, and it can be used as a pivot to produce zeros in these two spots here where the 1 and the -8 are. Let me see. Oh, do I have an error? Oh, it should be a half. Thank you. It's not 1/3 times row 3. Thank you, Mikhail. It's not 1/3. It's 1/2. Well done. Good catch. Good catch. You get a virtual candy bar for catching that. Okay, so there we go. Now this is our matrix, and look, I'm going to use the 1 to produce, I'm going to use that pivot to produce zeros where the 1 and the -8 are. So I'm going to take 8 times the third row, add it to the second row, put that result in the second row. And then, by the way, this here, what we just did here was scaling, by the way, in the previous step. So now you've seen all 3 types of elementary row operations that we use. So I'm going to take 8 times the third row, add it to the second row, put that result in the second row. Okay, that'll give me 0x1 plus 2x2 plus 0x3 equals 32. And then I'm going to take -1 times the third row, add it to the first row, put the result in the first row. That would give me then the first row would be 1x1 plus minus 2x2 plus 0x3 equals -3. You see how we do that? And we're not carrying the variables around. We understand we have an augmented matrix, but we don't need to carry those variables around. So these are all called row operations. And when you do your work, in your homework, or like, well, for the exam, at least for the first exam, I'd like to see you, I'd like you to tell me what row operations you're doing here. You know, write the steps out for me so that I know what row operations you're doing. and it'll be helpful for you too. Are there any questions so far? We're not done yet. We're not done yet, right? Because look here. Here's this -2 here. We can get a 0 in that spot, right? By the way, do we know what x2 equals? Do we know what x2 equals?
16.
X2 is 16 because second equation is 2x2. That's right, Yasin, very good. 2x2 equals 32. x2 equals 16. So we know x3 is 3. x2 is 16. Now we got to find x1. So what are we going to do? What's the row operation? What's the row operation to produce a 0 in this spot here? How would we write it? That's right, Mikhail. We would take row 2 plus row 1 and put the result in row 1. That's what we would do. We can't use row 3 because row 3 has a 0 in there, and that's not going to help us. So if we continue here, there's that. Oh, well, you know what I did? I guess I did, hold on. I guess I did something additional here. I left a, I mean, it's okay. It's okay. Hold that thought. What I did was, in this step here, let me just get this. What I'm doing is another scaling step. Another scaling step. I'm taking 1/2 row 2 and putting the result in row 2 so that I have a 1 in this spot here. See, it's always easier to work with ones than it is other numbers. So that's the next step I did. You don't have to do that, but it really helps. It really helps. Zeros and ones are our friends for row operations. But we're still going to do, now what we're going to do is to get a 0 in this spot here where the -2 is, we're going to take 2 times row 2, add it to row 1, and put the result in row 1. That's what we're going to do. And that breaks down the matrix. And remember, it's an augmented matrix. So it breaks it down, augmented. It breaks it down as much as you can do. This matrix is what this augmented matrix is. Hold on, let me just one moment. This augmented matrix is in what's called reduced echelon form. That comes up in section 1.2, and we'll get into that a little later. But basically, if we take the augmented matrix now and put it back in equation form, I mean, does it get any better than this? Does it get any better than that? I mean, can we really do anything more? No, and we wouldn't want to, right? I mean, we can just read off the solutions here. X1 equals 29, X2 equals 16, and X3 equals 3. And that's your solution. That's your solution. Are there any questions on this before we stop our we'll talk a little bit more about section 1.1, but we've really covered most of 1.1. Are there any questions?
Yeah, I was just kind
Yeah,
of
David.
like, I understand the triangles, like you want to get the zeros, so you just read off the variables, but I wouldn't be able to know exactly which order to go. Like you made the pivot and then you did the zeros in a particular order. Can you explain that a bit?
Yes, so that's right. And there is no, I want to say this the right way. You could have done this differently, and you could have done different row operations and ended up with this result. Okay, I remember a long time ago I gave a test where the problem just like this, and one student got to the solution using, I think, 7 row operations, and another student got to the solution using 12 row operations. So depending on your row operations you do, you could get to the solution a different way. But this is the most efficient way to get to the solution. What you want to do is, let me just blow this up here. You want to work downward to get zeros in the bottom left-hand corner of your matrix. That's a triangle of zeros. And then you work upward. You then work upward so you can get zeros in this top triangle. That's generally the most efficient way to get the answer, David. That's generally the best, most efficient way. So if you if you think about using that strategy, you'll be doing it the most efficient way. Is that okay? Excellent, excellent. And this solution, the point lies in all 3 planes. It lies in all 3 planes. So the 3 planes intersect in 1 point. Yeah, Mikhail, a question?
Yeah, so so the most efficient method you just described is, so like for the first parts,
Yes,
it's
I'll go back
down,
here.
then right, or is it right, then down?
Well, what you want to do, okay, that's a very good question. I think I can clarify that a little bit. So what I wanted to do, and let me put this, I wanted to get zeros in these 2 spots below the 1 in the first column. In the second column, I wanted to get a 0 in that last spot. That was my guiding force to determine what row operations I did.
So the method you described was down, then right.
I guess you could think of it like that. Yeah.
Okay. Okay.
It's
Thank
called
you.
the forward phase. Now the backward phase goes the other way. I want to get zeros in these 2 spots above the 2, because remember, these are where my coefficients are, on the left there. And then I'm going to want to get a 0 in this spot. That's called the backward phase. So you move downward and then upward. Okay, is that
Okay. Thank you.
okay? You're welcome. You're welcome. All right. Well, I'll go ahead and stop the recording here. Let me go ahead and stop the recording. Excellent.